Hi everyone, my name is Valts Blukis and I'll present our work on few-shot object grounding and mapping for natural language robot instruction following. This work was done in collaboration with Knepper and Yoav Artzi at Cornell University. We study generalization in the task of following natural language navigation instructions in embodied interactive environments. In this example of the task, our agent is executing the instruction: go straight and stop before reaching the planter, turn left towards the globe, and go forward until just before it. This and other grounded language robotics tasks are recently addressed by building a learning model that maps observations and language to actions. The model is trained on a large dataset of instructions and demonstrations situated in diverse environments. A key problem with such a model is to extend it after training. If you give it an instruction that refers to an object that the agent has seen in the training data, then the agent can figure out which object in the image is being referred to and complete the task. However, if an unfamiliar object is mentioned, then the agent would neither know what the word itself means, nor be familiar with the object's appearance. There is a vast diversity of objects in the real world, some of them personal and unique to each one of us. And if you want to build robots that can solve useful tasks in our households, then it's important that they can understand references to new and previously unseen objects. We introduced three contributions to address this problem. First, a few-shot language condition segmentation module that maps an image, an object database, and a text string to a segmentation mask identifying the object that the string refers to. Second, we introduce an object context grounding mapping approach that builds contextualized maps identifying object locations and their instructed use. Third, we show how to integrate these components into a learning-based instruction following policy that learns the map representation jointly with generating actions. Let's go through one by one. The few-shot language condition segmentation model takes as input an image and a set of object references. For each object reference, it outputs a segmentation mask identifying that object in the image. It is also given an object database that consists of a set of objects, each with a set of images and a set of text descriptions. We can extend the object database with new images and text strings to enable the segmentation model to recognize and segment the new objects. This is something that an end user can easily do by taking a few pictures and describing the new object. We train the visual components of the segmentation module on an augmented reality dataset that consists of a large number of first-person observations with synthetically rendered overlaid objects. This data is cheap to create, and its scale and diversity allows generalization beyond specific object types. And it gives us ground truth segmentation masks for training. Our second contribution is formalizing object context grounding maps and proposing a method to build them. We project the segmentation mask that we computed earlier to a global reference frame using a pinhole camera. The resulting masks highlight where each object is in the overhead view. For each object, we encode the context in which that object is mentioned in the instruction into a vector, and then we combine each mask with its context vector to produce the object context grounding map. The map encodes each location in the world with a vector that captures the intended behavior near that location. But it does not reveal the type of object that's there, since we hide the object identities before processing the context vectors. Finally, we integrate our contributions into a learning-based instruction following policy for a physical quadcopter. Specifically, we use the position visitation network that predicts probability distributions over the environment, indicating where the agent should go, which is shown here in red, and where it should eventually stop, shown here in green. It uses these distributions to predict velocity commands. We train the map representations jointly with the policy in order to learn the optimal representations for the task. The result is, to our knowledge, the first learning-based instruction following system that can be extended to reason about new, previously unseen objects at test time, without any retraining or fine-tuning, just by adding pictures and descriptions of the new object. As an added benefit, the system produces interpretable alignments between text strings and locations in the world. This is a snippet of human evaluation results, showing that our approach significantly outperforms previous state-of-the-art, even when the previous approach has access to the unseen objects during training. Thank you. I'll be happy to answer questions in our interactive session.